In the spring of 1941, a team of American engineers stood in front of a panel of military officials and watched their life's work get rejected in under 10 minutes. They had built what many considered the most advanced piston aircraft engine in the country. 48 valves, all aluminum construction. Dual overhead camshafts on every bank. A machine so precisely engineered that the officials examining it could not find a single flaw in the design itself. And they said no anyway. What happened to that rejected engine over the next 3 years is one of the strangest accidents in military history, because the very thing that got it thrown away from the sky is the exact reason it became nearly impossible to stop on the ground. This is the story of an engine that failed at everything it was built to do and somehow ended up saving thousands of lives because of it. Stay with me, because the ending of this story is going to make you look at failure completely differently. It starts with pride. Henry Ford had spent years watching a British company dominate a field he believed Americans should own. Rolls-Royce had built something called the Merlin, a 12-cylinder engine so good it was already flying inside the two fighters that would soon decide the fate of an entire war. Over 1,000 horsepower, liquid-cooled, constantly improving with every new version that rolled off the line. Ford wanted a piece of that. He approached the British company directly and asked to build the Merlin under license on American soil. The answer was a firm no. Rolls-Royce was not about to hand its most valuable secret to an outsider, especially not to an American car manufacturer they saw as beneath them in the world of aviation engineering. Most men would have taken that rejection and moved on. Henry Ford was not most men. He decided that if nobody would let him build their engine, he would simply build a better one himself and shove it in their faces. What his engineers produced over the following months was staggering. A 12-cylinder monster designed from scratch to match the Merlin's displacement, but exceeded in nearly every other category. 60-degree V configuration, every major component cast in aluminum, from the block down to the crankcase, which was almost unheard of for an engine of this scale at the time. 48 valves total, driven by camshafts sitting directly above them with no rocker arms, no push rods, nothing standing between the cam lobe and the valve itself. This was race car engineering applied to a wartime aircraft engine, years before that kind of precision became common practice. When Ford finally rolled this creation in front of the United States Army Air Corps in 1941, the reaction from the engineers examining it was genuine admiration. They understood exactly what they were looking at. In terms of raw sophistication, it was arguably the most advanced aircraft engine any American manufacturer had ever produced. And it did not matter one single bit, because sitting on the other side of the room was an engine called the Allison V1710. And while it was not nearly as elegant or as clever as what Ford had built, it had something Ford's masterpiece did not have: history. The Allison had been in continuous development since the early 1930s. There were spare parts stacked in depots across the country. There were mechanics who had rebuilt this exact engine hundreds of times with their eyes closed. There was a supply chain that already worked, tested, proven, moving. Switching to Ford's brilliant but completely unproven design would have meant tearing that entire infrastructure apart and rebuilding it from nothing, in the middle of a war that was rapidly becoming the largest conflict the modern world had ever seen. The Army Air Corps made the only decision that actually made sense. They stayed with what they knew. Ford's 12-cylinder engine, with all its genius packed into 48 aluminum valves, received no contract. None. It simply went nowhere. Now here's where most stories like this one end. A brilliant idea, crushed by bureaucracy, forgotten in a warehouse, a footnote nobody reads. But this story does not end there, and if you stick with me, you're going to see exactly why this rejection turned out to be one of the luckiest accidents of the entire war. Because Ford had made one very expensive and very stubborn decision before that meeting even happened. Convinced the contract was already his, he had purchased the tooling and casting equipment needed for full production of this engine ahead of time. That investment now sat completely idle in Dearborn, representing a massive sum of money and an enormous amount of specialized manufacturing capacity attached to an engine with no customer and seemingly no future. Picture that for a second. Rooms full of custom machinery built for one specific purpose, and that purpose had just evaporated. Most companies would have written it off as a total loss and moved on. Ford could not bring himself to do that, and honestly, neither could the men who had built the thing. The disappointment in Dearborn was real. The engineering had been exceptional, and it had been rejected for reasons that had absolutely nothing to do with whether the design itself was good. While that rejected engine sat gathering dust, something completely unrelated was starting to go badly wrong in the deserts of North Africa. And this is where the two storylines are about to collide in a way nobody in that Dearborn factory could have predicted. By the middle of 1942, American Sherman tanks were rolling off production lines faster than ever, but the engine powering most of them was becoming a serious liability. The standard power plant was a 9-cylinder air-cooled radial engine that had originally been designed for civilian aircraft, not for pushing 35 tons of steel across a battlefield. It produced somewhere around 350 to 400 horsepower, which was already marginal for the job, but that was not even the worst part. This engine had a nasty habit of fouling its own spark plugs. The lower cylinders, sitting at the bottom of the radial arrangement, would collect oil that drained down under gravity whenever the tank sat idle. And in combat, when a Sherman crew needed to fire that engine back to life after even a brief stop, those fouled plugs could mean the difference between escaping and dying where they sat. Facing German panzer units in the open desert, that was not some minor inconvenience. That was a matter of life and death, and everyone in those tanks knew it. The army scrambled for a fix. Their first attempt was almost comically desperate. Someone at Chrysler had the idea to weld 5 separate 6-cylinder engine blocks onto a single shared crankshaft, creating a bizarre 30-cylinder contraption that somehow ended up producing less horsepower than the engine it was supposed to replace, while being dramatically more complicated to work on. Mechanics in the field described trying to service this thing using language that has, thankfully, not survived in any official written record. But you can imagine the tone. Reaching certain parts of the engine meant removing entire other components just to get access. It was a nightmare wrapped inside a compromise. And the United States Army never fully embraced it. The Marines had their own separate solution using twin diesel engines, which worked well enough for their specific amphibious needs, but it did not solve the fundamental problem facing the broader Sherman fleet. What the Army actually needed was simple to describe and brutally hard to deliver. One single, powerful, liquid-cooled gasoline engine that could push a 35-ton tank across brutal terrain without fouling its plugs, without demanding a team of specialists just to keep it running, and without dying at the exact moment survival depended on its starting. And in 1942, someone in the Army finally made a phone call that nobody expected. They reached out to Ford. Here is the twist nobody saw coming. The message from the Army was almost insulting on its surface. They did not want Ford's brilliant 12-cylinder aircraft engine. They wanted an 8-cylinder tank engine, and they wanted it fast. But then someone in Dearborn looked at the math, and everything changed in an instant. Ford had already built the tooling. Ford had already built the casting equipment. All of it was sitting there, paid for, unused, gathering dust from a rejected aircraft program. What if you simply removed 4 cylinders from the 12-cylinder design? The 60-degree V angle stayed exactly the same. The bore and stroke dimensions did not need to change at all. The dual overhead camshaft system could be adapted onto the shortened block with relatively minor modification. The gear-driven accessories, the dual ignition system, the entire all-aluminum construction philosophy, all of it carried over almost untouched. What emerged from that calculation was a new engine entirely, and it would go on to be called the Ford GAA. Now pay close attention, because this next part is the heart of the story, and it is the reason this so-called mistake ended up being one of the most important engineering decisions of the entire war. The finished 8-cylinder engine displaced 18 liters. And that single number placed it in a category all its own. To this day, it remains the largest all-aluminum gasoline vat ever put into production. Its bore measured over 5 inches and its stroke ran 6 inches, dimensions that engine builders today would associate more with heavy diesel industrial machinery than with anything meant to move fast. The block was cast as a single piece of aluminum with hardened steel sleeves pressed into each cylinder to give the soft aluminum something durable to grip against. The valve train kept all 4 overhead camshafts inherited directly from the failed aircraft design, driving 32 valves total through precisely machined components with no rocker arms and no push rods anywhere in the system. This was closer to race engineering than anything else coming off an American production line in the entire decade. Twin carburetors fed the engine through a cross-flow induction path that pulled air in from the outside of each cylinder bank and pushed exhaust straight back out, an arrangement built for efficiency, not for cutting corners. But here's the part that should stop you in your tracks. The compression ratio was deliberately kept low, tuned to run on regular military-grade fuel, rather than the higher-octane aviation fuel that would have unlocked far more aggressive tuning, and even held back like that on purpose. The factory rating still came out to 500 horsepower. The torque figure was even more absurd. Over 1,000 pound-feet available from almost the very bottom of the power curve. The kind of raw, low-speed force that could rip a Sherman free from a mud bank, or drag it up an incline that would leave a lighter engine straining against the mechanical limits of its own pistons. Because this engine had descended directly from an aircraft design, its internal assembly followed aviation standards rather than typical automotive shortcuts. Safety wire was threaded through the heads of critical fasteners throughout the entire engine, a practice borrowed straight from aircraft manufacturing that made sure no bolt could ever vibrate loose during sustained operation. Each forged aluminum piston carried 5 rings instead of the usual configuration, a specification you would expect to see on a high-performance racing engine, not standard military hardware rolling off an assembly line by the thousands. Think about what that actually means. An engine built to survive high-altitude flight, engineered with aircraft-grade tolerances and safety margins, was now sitting inside a ground vehicle doing a fraction of the work it was designed for. It was, without anyone fully realizing it, dramatically overbuilt for the job it had just been handed. Production began at Ford's Lincoln plant on the west side of Detroit in 1942. And here's the beautiful irony sitting right at the center of this entire story. The exact same casting cores from the abandoned 12-cylinder aircraft program, the tooling that had represented a painful, expensive failure just months earlier, immediately started producing parts for this new engine. Nothing was wasted. Tooling that would have otherwise been written off completely began churning out components for a machine that finally actually had a customer. The M4A3 Sherman variant, the one equipped with this repurposed aircraft engine, went into assembly in May of 1942, and it quickly became clear that the Army knew exactly what they had. This specific variant was held back for American use rather than being shipped overseas to allies through Lend-Lease. Other nations received Shermans running the diesel engines or the ugly multi-bank Chrysler contraption. American crews got the one built from a failed fighter plane engine, and the difference showed almost immediately. Testing conducted through 1943 compared service intervals and failure rates across the different Sherman engine configurations under real operational conditions, and the numbers told a clear story. The version running this repurposed aircraft engine consistently outperformed the alternatives in reliability, in a war where a single tank might need to cover 60 miles of ground in one day of advance. The gap between an engine that reliably lasted through extended operation and one that constantly broke down represented something far more important than a statistic on a chart. It represented men who came home instead of men who got stranded in the open, exposed, waiting for a rescue that might not arrive in time. And if you think the story stops being interesting there, wait until you hear what was happening on the other side of the battlefield. Because the contrast is almost unbelievable. The Germans were fielding some genuinely impressive tanks during this same period, machines with engines that looked incredible on paper. A 23-liter cast iron V12 producing roughly 700 horsepower powered both the Panther and later versions of the Tiger. On paper, those are strong numbers. In the field, the story was a disaster. The Panther was rushed into combat at the Battle of Kursk in the summer of 1943 before its mechanical issues had even been resolved, and more than half of the Panthers committed to that offensive broke down from mechanical failure before enemy fire ever got the chance to touch them. Half, before a single shot mattered, half the fleet was already out of the fight because of engine and drivetrain problems. The lubrication system on that German engine was vulnerable to overheating under sustained high-speed operation, and a related weakness in the tank's final drive compounded the problem by failing under the sheer stress of the vehicle's own weight. Even after the war, when the French military got their hands on captured Panthers and tested them under completely non-combat conditions, they still found the tank mechanically unreliable. Crew handbooks for the Tiger's earlier engine variant carried explicit warnings against pushing revolutions past a certain point, because doing so risked catastrophic failure. Now here is the detail that should genuinely blow your mind. The American engine, built from a rejected aircraft design, was governed to that exact same speed limit, but not because it was fragile. It was held there simply because more power was not necessary for the weight class it was pushing. One engine was capped out of desperation to survive. The other was capped because it had so much extra capability that nobody needed to unlock the rest of it. The construction philosophy told the same story from a different angle. The German engine used a cast iron block, heavier and considered more conservative by the engineering standards of the era. The American engine, built from failed aircraft ambition, used an all-aluminum block that was lighter, dissipated heat more effectively, and demanded significantly tighter manufacturing tolerances to produce correctly. In a production military engine, Ford had accidentally achieved a level of sophistication that most European manufacturers were still reserving exclusively for aircraft. This same engine also found its way into the M10 tank destroyer, a fast, lightly armored vehicle mounting a powerful gun on an open turret, and it powered that platform with the exact same effortless reliability it brought to the Sherman. Crews trusted it completely without hesitation because it simply did not let them down. That trust translated directly into results on the battlefield, because reliability alone does not win wars. Reliability combined with the right moment absolutely does. During Operation Cobra in July of 1944, The offensive that finally broke American forces out of the brutal hedgerow country of Normandy and into open terrain. Sherman units equipped with this engine were able to sustain a pace that pushed every mechanical component in their drivetrains to the absolute limit, and they held together. While German commanders were forced to manage Panthers and Tigers that required delicate, careful handling to avoid catastrophic mechanical breakdown, American units simply kept moving. A tank that runs is a tank that fights. It sounds almost too simple to matter. But that single principle decided the outcome of countless engagements across the entire European theater. It was not always about who had the bigger gun or the thicker armor. Sometimes the deciding factor was as basic as which engine actually started when the crew turned the key. But the most remarkable part of this entire story is not what happened during the war at all. It is what happened decades after it ended. And if you have made it this far, this next section is genuinely worth staying for, because it reveals just how much untapped power was sitting inside this engine the entire time, hiding in plain sight. Unused. Remember, this engine had spent the entire war operating at a fraction of its true capability, deliberately restrained by military specification, because raw aircraft-level horsepower was never actually the requirement for a medium tank. The 500 horsepower rating and the governed engine speed were never the true limits of what this machine could do. They were simply the numbers the army needed, nothing more. When mechanics and enthusiasts started tearing these engines apart in the late 1940s and into the 50s, they discovered something extraordinary sitting inside. There was an enormous amount of untapped energy still waiting there, completely unused. Legendary land speed racer Art Arfons, the man who would later shatter multiple world records at the Bonneville Salt Flats, had early hands-on experience with this exact engine through his work-building competition machines. Racing mechanics who took these engines apart in search of more power found that the internal components showed almost no wear or stress even at the governed military output levels. Every component from the forged aluminum pistons to the oversized crankshaft bearings had been engineered originally for the brutal demands of a high-altitude aircraft engine, and here it had been sitting inside a tank, running at barely 60% of what it was actually built to handle. The first major milestone these post-war engineers crossed was 1,000 horsepower, and shockingly, they got there with relatively simple modifications. Advancing the ignition timing, improving exhaust flow, and switching to higher octane fuel than the military specification had ever demanded. At that output level, the stock internal components showed no signs of impending failure whatsoever. This engine had been built from the very beginning with enough structural margin to handle double its rated military output without asking for anything extra in return. Later builds pushed even further by adding forced induction. A supercharged or turbocharged version of this engine responded to boost pressure with the exact same composure it had shown decades earlier under normal atmospheric conditions. The stock pistons proved reliable up to roughly 1,200 horsepower before the piston rings finally started showing stress. Swap and upgraded pistons strengthened the valve springs, bolt on a turbocharger, and builders were reliably crossing 2,000 horsepower. This engine found an unexpected second life in post-war tractor pulling competitions, where modified agricultural machines competed to drag weighted sleds using raw torque alone. The exact same low-end grunt that had once dragged Sherman tanks out of mud translated perfectly into a competition built entirely around maximum pulling force at low shaft speeds. And in Brazil, where mechanical creativity in motorsport has an incredibly rich tradition, builders pushed this engine even further than anyone in America ever had. One fully modified example: running computerized ignition, direct fuel injection in place of the original carburetors, and a twin turbocharger setup at moderate boost, has been documented producing 1,500 horsepower while holding together completely. At higher boost pressures, builders have recorded outputs approaching 3,000 horsepower. And at that point, the only real limit is whichever specific components the builder chose to reinforce or leave stock, not any fundamental weakness in the original architecture from 8 decades ago. The flat-plane crankshaft that Ford's engineers originally specified purely for aircraft-level performance characteristics turns out to be exactly what modern high-output turbocharged applications need. A design choice made for a fighter engine that never flew ended up being perfectly suited for a completely different kind of extreme performance that would not exist for another 60 years. Now sit with this for a second, because this is the detail that ties the entire story together, and it is the reason this whole thing deserves to be called a mistake that changed everything. The engine that carried the Sherman through Normandy, across the Rhine, and through the final brutal campaigns of the war in Europe, was running at perhaps half of what it was actually capable of producing the entire time. Every Sherman that broke through an enemy position, every tank destroyer that provided cover for advancing infantry, every single one of them was being powered by an engine that was deliberately holding itself back, restrained on purpose because raw horsepower was never the requirement. What the Army needed was reliability, and reliability that would last through months of brutal, relentless use. This engine delivered both, with margins so wide that even the men who designed it probably could not have fully predicted them. Back when they were cutting 4 cylinders off a rejected aircraft program in 1942, and simply hoping the Army would find the result acceptable. Henry Ford set out to build something that would embarrass Rolls-Royce and win a lucrative aviation contract. He failed at that goal completely, and there is no soft way to put it. The engine he built never flew. No fighter plane, no bomber escort ever drew power from those 48 aluminum valves in the sky the way he intended. The contract went to a competitor, and his 12-cylinder masterpiece went into storage, seemingly for nothing. But the engineering behind it, the gear-driven accessories, the 4-valve cylinder heads, the all-aluminum construction, the dual ignition system, the flat plane crankshaft, the safety-wired internals built to aviation standards, none of it disappeared. It survived the rejection completely intact, waiting, and when the Army came back 2 years later looking not for an aircraft engine, but for a tank engine, every bit of that engineering came along with it. Ready and waiting to be used for a purpose nobody had originally intended, this engine never conquered the sky, the one thing it was actually built to do. Instead, it conquered the ground, carrying 5 men across thousands of miles of the most contested and brutal terrain in modern history. Starting reliably every single time they turned the key, through mud, through frozen fields, through streets shattered by artillery, never once giving those crews a reason to doubt it, or wish they had something else under the hood. A rejected aircraft engine built out of stubborn pride and wounded ego ended up becoming one of the quiet reasons an entire generation of American soldiers came home. Sometimes the biggest mistake in the room is not actually a mistake at all. Sometimes it is just an answer to a question that has not been asked yet. If a story like this one, where failure quietly turns into one of the most important decisions of an entire war, interests you, there is a lot more where this came from, and the next one might surprise you even more than this one did.